Physics is all around us. We live and we breathe it. Everything around us follows a certain set of rules that we've become accustomed to. This to me is the intrigue of quantum physics because it follows an entirely different set of rules. A shining description of this foreign playbook is seen in the double slit experiment. When I first came across this experiment, I was engrossed and I did a considerable amount of research, and even more in preparation for this presentation, utilizing many sources from articles to journals. The double slit experiment is a mind-bending, yet perfect example of basic quantum phenomena. To best inform you, I'll begin by describing basic quantum physics, the nature of light and electromagnetic radiation, Schrodinger's wave equation, and then finally describe the double slit experiment and the accompanying which way experiment. So, let's begin by defining the term quantum physics. Quantum physics is the branch of science and theories which attempts to describe the nature, physical properties, and phenomena of matter at the quantum level, that is, atoms, particles, and subatomic particles. Light is just such a particle, and has been the subject of frequent study by scientists. And the nature of light has been a subject of debate for centuries, really. Is it a wave? Is it a particle? Nobody really knew, because light had been observed to act as both. For instance, Einstein demonstrated that light acts as a particle in the photoelectric effect, where a singular packet of light or a photon may strike a material and fling an electron out from it, which would indicate that light is a particle because it bumped that electron out of orbit. However, in the double slit experiment, which I'll describe shortly, light is very clearly acting as a wave, sometimes. You'll hear about that very soon. This wave-particle duality, which is called, is a key to understanding the quantum realm. It can be said that when something is acting as a wave, that is, when a particle is acting as a wave, it is existing in a state of probability, and when it's a particle, it is existing physically. This concept leads directly into a fundamental tenet of quantum physics, the wave function. At our scale, everything acts very different from the quantum realm. So, take example, a car speeding down the road. The car is there, the car has a definite speed, definite properties, all that. However, in the quantum realm, nothing really follows these rules. It's all probability that something could exist or could have certain properties. And once we measure it, that's when everything falls into place. And that is what the wave function describes. The current understanding is that at the quantum level, particles can't be said to have a certain position or certain properties until they are measured. And when particles are not under measurement, they exist in a state of probability that they could be in a certain place or could have certain properties. And this Schrodinger's wave equation is a function which accurately describes the probability that a particle could be found at a certain point and have certain properties. When this measurement occurs and the particle goes from a state of probability to actually existing physically, it can be said that it's called the waveform collapsing, which means that Schrodinger's equation collapses, and the particle instantaneously exists, not as a wave, but as a particle, when it's measured. And this is precisely what occurs in the double slit experiment. According to the 2019 paper by Jonathan F. Schoenfeld, Analysis of Double Slit Interference Experiment at the Atomic Level, in 1974, Italian physicists Merli, Miseroli, and Pazzi set up a device which emitted electron beams in front of a screen with two narrow slits in it, hence the name double slit experiment. The device could either fire beams of many electrons at one time or one at a time. The particles would be fired at the screen and then would pass through either slits and then strike a detector screen which would record their impact. And as many electrons piled up, it would show patterns of where they struck the screen. So, when they fired many electrons at a time, something called an interference pattern emerged. That looks like this. This occurs when the electrons, acting as waves, interfere with each other as they go through the slits. So the troughs and crests of the waves combine and alter the paths into this orderly pattern there. So that's when they're acting as waves. Next, the scientists fired one electron at a time. And since they were going through one at a time, they expected there to be two solid bands because there was no other electrons to interfere with each other. So they would just pass straight through and strike the normal places. But that's not what happened, because when they went through one at a time, the interference pattern still remained. So that makes no sense. What is this single electron interfering with? Is it interfering with itself? This is the hypothesis that has gained steam and become fundamental to quantum theory. That not only was the electron passing through, or not only was the electron in a probability state, its other probability states were interacting with each other. So this means the probability wave of the electron going through one slit was interacting with the wave of probability that it may have been going through the other slit. So it was in a superposition, they call it, of going through both slits at once and interacting with itself to create the interference pattern. This question naturally led the scientists to try and verify. So they set up detectors at the slits and performed what is called the which-way experiment. They wanted to find out if the electron was going through one, if it was going through the other, or going through both. That's what the detectors were there for. So when they set up the experiment and started firing the electrons, be it one at a time or many at a time, now, since they were being detected, there were two solid bands formed. So the waveform collapsed just by measurement, which is, honestly, just take a moment to think about how crazy that is, that just because something is being detected in that little quantum world, things act different. So, this experiment was repeated over and over and over to the same results. So, the act of measurement changed the behavior of the electrons, which is crazy to me, and probably to you guys. So, this boggled the scientists' minds, and they wanted to figure out if they could find a way to maintain the waveform, which is maintain the wave and interference pattern, while also finding out which slit the electrons went through. So what they did is they introduced quantum entanglement into the situation. This means that they used essentially two prisms which would split the electrons into two electrons of half the energy of the first. And entanglement is when two particles share the same properties. So if you measure the properties of one, you know what the other one is doing. So it would fire through the gun, go through the slits, and then if it went through A, it would go through prism A and split, and the entangled proton or electron would go to detector A, and the opposite with B. So, yeah. So, even though they weren't measuring the physical electron that was going through the slits, they were measuring the entangled one, the waveform collapsed and was left with two solid bands, which means that the electrons knew they were being measured, even through time and space. But they were determined to thwart the quantum physics, so what they did was they scooted the detectors back behind the screen so that the electrons would go through the double slits, either one, and hit the back screen before its entangled partner would be observed. So, because effect precedes cause, and because um, information can't travel backwards in time, that should have been completely, foolproof. Electron hits the screen, then hits the detector. The detector tells us what happened. But that's not what happened. The information did travel backwards in time. There's many explanations to that somehow try to explain it, but that's above my head too. So yeah, information traveled backwards in time, seemingly, and formed two solid bands on that screen, meaning the waveform collapsed and it knew it was being measured after it had already hit. So that is super duper crazy and probably very confusing and long-winded. So this has been my informative presentation on the mind-boggling double slit experiment. To do this justice, it was necessary to define quantum physics, look at the nature of light, and then move on to the double slit experiment and Which Way experiment. I hope you walk away with a little taste of quantum physics, and maybe you'll do some research for yourself and figure out more cool stuff. So this concludes my presentation. Thanks for listening.